In this lecture, I want to talk about custom deleters for unique and shared pointers. As we've seen, unique and shared pointers manage the deallocation of the managed heap object, but we may want to define how the managed heap object is deallocated explicitly, and to do that we can define a callable custom deleter. The custom deleter can be a function, a lambda, or even a functor. This custom deleter will be invoked when the smart pointer gets destroyed. The custom deleter is going to take in a pointer to the managed heap object, and we can use that custom pointer to access the member functions, of course, and also to call delete on that. If we use a custom deleter, then of course we need to ensure that we're actually going to allocate the heap object that otherwise would have been managed by the shared pointer or the unique pointer. So we need to take care of that deallocation ourselves then. Here's the syntax. We have the shared pointer. We'll start off with the shared pointer because that's a bit easier. You have the shared pointer, you allocate an entity on the heap, and then you pass in the identifier for the callable deleter. So your custom deleter. The unique pointer is a bit more complicated. You also have to pass in not just the type argument for the managed heap object, but also the type of the custom deleter. And of course, as we've seen in the callables lesson, we can use the standard function to abstract things away, but we can also specify a pointer to a function or a function pointer, or maybe a functor type. But to make it a bit easier, we'll use the standard function. We'll see how we can set up a custom deleter for the unique pointer later on in the lecture. We'll start off with the shared pointer in the next demonstration. Sometimes when we are dealing with older or legacy code, those classes may not perform a proper cleanup job. You may have to invoke a special function to do a proper cleanup. For this example, I have this legacy entity class. It is going to manage an integer on the heap. Okay, so it's going to manage a heap object. I'm just using an integer instead of some other user-defined type just to keep it concise. Okay, so it's going to manage a primitive type, an integer. I pass in, it actually has a default argument of 1 for the construction, but of course we can pass in a value. In the private section, I have the member pointer, which is a pointer to an int. Then in the body of the constructor, I go and allocate an integer on the heap, and I pass in the parameter for the initialization of that heap object. Then in the destructor, all I do is I print this out, legacy entity destructor invoked. You can already see the problem with this. What we want in the destructor is, of course, we want to go and allocate that heap object that this entity will manage. And so because that is not in the destructor, I have this void release function. I'm going to print out managed heap object of legacy entity deallocated, and then also print this out managed heap object was, and I dereference the member pointer to fetch that value. And then I go and deallocate the heap object that is pointed at by this member pointer. This is just a high-level simple example. It is really going to depend on what you come across, but some older code may not do the entire cleanup process in the destructor, so I have to go and invoke an additional function, such as in this case release. So that is what we are going to do in the main function here. I go and instantiate the legacy entity, pass in 55 for the constructor, then I have to do entity.release before it goes and invokes the destructor when we finish executing the main function. So let me build and run that so we can see what we get. When I invoke the release member function, we get this managed heap object of legacy entity deallocated. The managed heap object was 55. Then when program execution reaches the end of the main function, then we get this legacy entity destruct invoked. If I comment this line out, we will get a memory leak now because we do not allocate that heap object, as we can see. So we never call this delete. Now, of course, in modern C++, you want to go and add that sort of code in your destructor. But again, sometimes when dealing with older code, you may not have that in the destructor for that class. So you may need to be explicit with your cleanup, as we are doing here. And it gets even more complex. So for example, if I allocate a legacy entity on the heap, now I have to do two steps. I have to invoke the release member function, and then I have to do delete entity pointer to deallocate the legacy entity on the heap. Build and run that, and you can see what I mean. Now I get, with the release member function, I get that invoked. Managed heap object of legacy entity deallocated. Managed heap object was 55. Then when we do delete, we get legacy entity destruct invoked. Moving on, let's say we want to use a smart pointer to manage the allocation and deallocation of a dynamic legacy entity. And we'll start by using the shared pointer because that's easier to work with. And now we have to think for a second, that the smart pointer is not going to invoke this function. Okay, it's only going to do new and delete. It will not invoke this release for us. So just keep that in mind. So if we do something like this now, that smart pointer is going to manage the legacy entity object on the heap for us. We do not go and deallocate the entity that the legacy entity manages. What you can do is you can go and invoke that now. But this is just a simple high-level example with one class. You can have many classes that have a similar sort of cleanup process, and of course if you have to go and invoke this each time, that will be time consuming. So instead of doing this, what we can do is we can define a function referred to as a custom deleter, and then we can pass it in here. For example, the custom deleter has this formal parameter. Okay, it matches the type as you can see, and that will have a raw pointer to the managed object. So what we can do with that is we can now go and do all of the cleanup tasks. We may want to write something out to disk or something like that. And then because we now have a custom deleter, we want to deallocate the managed heap object. And as I mentioned, with the deleter, we now have a raw pointer to the managed heap object. So I have to deallocate that now explicitly using this delete statement. And then we can go and pass that in here. That is where we construct the smart pointer. Okay, in this case, a shared pointer. I'll do comma, and then I can pass in the custom deleter. In this case, I just call that deleter. If you want to, you can do the ampersand, the address of operator, but as we've seen in the previous lesson, that is not necessary. You can actually also do a lambda here, but for right now, I'll just stick to this deleter. And I actually have to go up and make sure that I have the memory included for the smart pointers. Go and remove that, and I'll pass in this deleter. And because we do it in this way, we do not use the make shared or the make unique, as we'll see later. But for now, I'll build and run. Now we'll see that deleter will get invoked, and the managed heap object is deallocated. The integer on the heap that was managed by the legacy entity was 55. Then we get the actual destructor invoked for that legacy entity that is now managed by the shared pointer. As I mentioned, we can remove the ampersand over here, and this will still work fine. So now instead of passing in the deleter function, what I'll do is I'll create a lambda instead. And for this, I want to make some space. And basically, I'll do the same thing in here. That is in the lambda that we do in the deleter function. So as we can see, we have the lambda right here, and within that, we are going to do the same thing that we did in the deleter. So in this way, you can write a quick lambda. Instead of defining a special function for that, you can just have a nameless function. And as with the deleter function, we are going to do the cleanup with the release member function, and we are going to deallocate the legacy entity that is managed by the shared pointer. Again, we specify the object to allocate, and then for the second parameter here, we can provide a function identifier or a lambda, or maybe even a functor if you want. Build and run, and you can see that works as before. Next, we want to look at how we can set up a custom deleter for the unique pointer. So I'm going to continue with this example. I'm going to include the memory and the namespace standard here and the IO stream. Then I still have this legacy entity class and the custom deleter as before. But in this case, I want a unique pointer instead of a shared pointer. Now what we'll see is we'll actually get an error with this. So if I try and build, you'll get this sort of error. Can do Ctrl+Shift spacebar here. You can see we actually have a default delete. So basically what we want to do is we want to provide another parameter, which is going to be the type of the deleter. So let's just start off by providing a function pointer. The deleter is going to return void. And what argument does it accept? It's going to accept this right here. And remember, since this is a function pointer, we need to provide an extra pair of parentheses. We're not going to name it. We're not going to name the function pointer. We don't need a handle. We just want to specify that type right here. And then I can build and run. And that should work fine now. we get deleter invoked and everything works as before. Now instead of using a function, we can also go and define a functor if we want. And we're going to do the same thing as we do here. We're basically going to do the same thing that we do in here, right? And I'll just copy that. And now we have to specify that right here. Instead of specifying the type of a function pointer, I'm specifying this type right here. Something like that. And you can see I can build a run and that should work fine. We get the same sort of output, but now we are using the deleter functor instead. And to make this more generalized, we can pass in basically whatever we want. Of course, we can go and include the functional file, and then I can, if you recall, a function object is going to be a wrapper for a callable. I specify the return type, it's going to be void, and it's going to take in a pointer to a legacy entity like that. Press enter here so we can see what we have. This is the name of the instance for the unique pointer, and then this is what we pass in for the constructor, of course. So we allocate this legacy entity, and then we use a custom deleter. And now I'm using the functor. So if I build and run that, that works. We get deleter functor invoked and everything else. And I can also use the deleter that is defined up here. Okay, so build and run that, and that works fine. This is what I mentioned before by sometimes we have to write a custom reusable deleter, and with that we can go and perform whatever cleanup task we need to do. Instead of trying to modify existing code to do the cleanup as you want, you can simply use a custom deleter, and they are reusable as we can see here as well. Okay, a few final notes on this. We've seen what we can add for the constructor. We allocate a new entity on the heap, and then also we pass in whatever deleter we want. So I'll just go and press backspace again. And now we have this long type, right? If you think back for a second to type definitions and type aliases, we can create a type alias or a type definition for this. It is really going to depend on the conventions and so on. I really don't want a long name here. So I'll just do a prefix, DUP for deleted unique pointer, underscore legacy entity. I can now copy that, paste it here. Actually, that should be UP for unique pointer. So this unique pointer is now of this type, and the type definition or type alias is an alias for this type. Build and run that. And that should build and run without any issues. Next, we can also use the type alias. That is with the using keyword. I will comment out the type definition and I'll give this the same name. End that off with a semicolon, and because we are using the type alias here, we can do a template. But actually before we do that, we'll just build a run. And that is still working just fine. And now we can make this even more generalized, so I can pass in T here and also T. Remember, the deleter is going to accept a pointer to the managed heap object. That is the object that the smart pointer is going to manage. We specify that here to the left, and so we also pass in a pointer to that type for the standard function object. Now we'll get a warning down here, so we have to specify that type. And of course that is going to be this legacy entity. That is now going to be the type argument for this type alias. And I can build a run just one more time and that's going to work. And then what we can also do is we can make the deleter more generalized as well. I'll go up and I'll use the deleter function right here as a demonstration. And now this is a more generalized deleter, but you have to make sure that you remember with an array that you want to create a special deleter for that particular case. This is not going to work for an array. Now of course we'll get this red squigglies again. Take a second if you don't understand why. Okay, of course we've just converted this deleter to a template, so we have to pass in the type now. We can build a run, and you see we still get deleter invoked, so that works fine. But now I can also use that deleter on some other legacy entity, or wherever we need that. For example, if I had another class like this, legacy entity, copy that, paste that down here, and in this case I'll just call it entity. That now also has the release member function. Those need to be the same, otherwise you'll need to go and overload this particular deleter or create another one. But what we can do now is copy that, create a unique pointer with a special deleter, so a deleted unique pointer, to some legacy entity, and in this case we just pass in entity actually, and that's going to allocate, or in other words manage an entity on the heap. And then for the deleter we now pass in entity, and I'll just pass in something else for the constructor, such as 33 for example, and actually that is the same name now, so I'll have to rename that, build a run. Now we get that deleter invoked twice. The first time the manage heap object of entity is going to get allocated, and then the manage heap object of legacy entity deallocated. Okay, member was 55, for the entity it was 33, so we can also see those destructors get invoked for entity and legacy entity respectively. And we don't get any warnings or errors here. The point of this is we can now create more generalized deleters, but also make use of the templated type aliases to create type names that are easier to read but that are still templated. This is not something that you'll see all that often. I'm just showing you a few tips and tricks here. And as I mentioned before, I generally avoid type definitions or type aliases, because if someone else comes along and they have to read my code, then they have to go and look at what that actually is. But of course with IntelliSense and so on, that's not that difficult. You can do Control-K, Control-I, and that should give you that right here in the IntelliSense helper. So again, it's all about personal preference and then also the company conventions. To wrap up this lecture, just a couple more things to keep in mind when you are using custom deleters. So I'm using the functional file and the memory file again for this, and then I have this custom deleter function. This time we'll just use the fundamental type, the int, and then I'm going to delete the heap object that the smart pointer is going to manage. Again, we pass that in, so I'm just going to delete that. Then I also have a deleter functor. I overload the function call operator, and I do the same thing, I delete the parameter. Now in the main function, I'll just scroll a bit here so we can see what's going on. In the main function, I'm going to do a couple of console output statements, and I'll do the size of, and I'll do the size of the unique pointer, and I pass in int for each one of those, but the second type argument is going to be different. So I'll start off with the function. As I mentioned throughout the lecture, this here is easy to use, but there are some trade-offs to that, as we'll see when we build a run. And then I'll do the size of, I pass in int, and here I simply have a function pointer. So you should already start to think that, okay, this is going to be cheaper to use than this function. Of course, we are not really concerned with how the function works internally, but a pointer is typically cheaper. Alright, and then we have this one right here where I pass in the type of that deleter functor. Of course, we are not passing in the function, for example, the identifier of the function. We are working with types here. These are type arguments, alright. And finally, I have this one, size of, unique pointer, passing in for the type. We do not provide a second type argument, so this is going to use the default deleter. And if I build around that, you may be surprised with the results. We get 72 here. That is much larger than the other results, including our functor and the one with the default deleter as well. And even the function pointer is a bit larger. The point of this demonstration is use this sparingly. You can use it. It is there to make your life easier, but it is a bit more expensive, as we can see. Now I'd also like to do a lambda, for example. And maybe the parameter is going to be a pointer to a double. And I need the equals there. And that is a lowercase p, not an uppercase. Copy that. So we can do the size of, and what we pass in here now, that is for the second type argument, because we want the type of the lambda and it's currently different than these other ones, right? So how can we sort of get the type of that lambda function? Well, what we can do is we can use the declare type or decl type. and then we can pass in the lambda identifier. I haven't covered this before, so pay attention to this. I'm not invoking the lambda right here. If I invoke it like this, okay, we don't want to do that. What we want to do is, we want to specify the lambda identifier, and that is going to give us a type back. You can do something similar with a function. So for example, if we want to pass in the type of the deleter function, but we do not exactly know what the return type and the parameters are, for example, we want some quick way of determining that, then we can pass in that deleter right here. But with that, if we build now, we should actually get an error. So I'll just build that. And yeah, we actually get an error here. And that is not particularly helpful. So, but the point here is what we need to do is we need to pass in the reference. Okay, so we need to be explicit with that. We pass in the ampersand followed by the function name. Okay, now we should be able to build and run just fine. And you can see we get 16 printed out twice now. And I'll just go and remove that. Pass in the lambda, we're not going to invoke it, we just pass that identifier in. And then build and run. And you actually get an 8 with the lambda, as we can see. So that is also cheaper than the unique pointer with the function type. Also with the functor, let's say I have a functor with a state. So what I mean by that is we have the struct here, and with this type we have two doubles. Just as a silly example, that functor has two doubles to keep track of some state, and then this right here will no longer be 8, it will now be greater than 8. So let me just build and run that. You can see it's now 24 actually. Okay, so just keep that in mind. Your stateless functors will use less memory than the ones that have a state. Okay, that was just a quick bonus section for you. Hope you find it interesting. And with that, we're actually going to wrap up this lecture. I'll see you next time.